Hello, in this video we will be taking a look at a sample problem that deals with material balance as well as the dynamics of material balance. And we will also be dealing with proportional control, setting up a proportional control system for the material balance, in this case specifically for fluid flow. Now this sample problem here has rather simplified numbers, so as you can see the cross-sectional areas here are pretty simplified and not realistic to a real-life scenario, but the complex critical thinking that we will be talking about can be applied to chemical engineering applications in a wide variety of industries. So we're given this problem here, and it says that we have three tanks with cross-sectional areas of 0.51 and 2 meters squared, and they are interconnected at their bottoms with initial fluid heights of 0.5, 1, and 2 meters respectively. It says that the magnitude of flow between the tanks is proportional to the square root of the difference in fluid heights between pairs of tanks, and the proportionality constant between the tanks 1 and 2 and tanks 2 and 3 are both 0.1 respectively. Tank 3 drains to the surrounding height of 0 with the same proportionality constant. And then it says, using the simplest form of control for the fluid level in the third tank, which is proportional control, which I'll talk about in a minute, the flow into the second tank is set equal to the proportionality constant, again 0.1, multiplied by the difference between the fluid level set point for the third tank and its actual fluid level. So in part 1 here, it says to derive the differential equations in order to solve the fluid level in the three different tanks. And then in part 2, what we'll have to do here is we'll have to simulate the dynamics of this controlled three-tank system by solving the differential equations that we have derived in part 1, then using something called, as you see here, scipy.integrate.solve IVP, which essentially is a way to solve a initial value problem in Python. So we'll go ahead and be able to plug in the differential equations that we have set up. But first here, what we're going to jump into next is this part 1 here. So I'm going to go ahead and draw this problem out so we can have a nice visual. And I'll go ahead and explain just exactly what's going on visually so that we can see what's going on. And we'll need to, from there, figure out the flow between tanks 1 and 2, tanks 2 and 3, the flow in, the flow out. And also we'll need to figure out the change in volume of the tanks, which will actually incorporate our differential equations so that we can solve this problem. So let's go ahead and jump into part 1 and talk about how we can derive expressions in order to solve this problem. Okay, so I've gone ahead and drawn out a picture of what this problem looks like. So here we'll have the initial flow, so Q in going into the second tank. So here we have tank 1, tank 2, and tank 3. And just to go through the different variable names that I've given here for this problem, H1, H2, and H3 are the three different heights of the three different tanks. And you'll see at the top here I have AC1, AC2, and AC3. This is the cross-sectional area for the three different tanks. So first here to start, we want to look at the flow from each tank into its successive tanks. So the flow from tank 1 into tank 2, and then the flow from tank 2 into tank 3. We'll have to first take into account the difference in height between those two tanks. So here if I write out Q1 comma 2, so Q being flow, and then 1 comma 2 meaning the flow from tank 1 to tank 2. And again, taking into account the difference in height between the two tanks, we'll say H1 minus H2, so the height of the first tank minus the height of the second tank. And we'll have to take the square root of that or raise it to the 1/2 power. And this here will be multiplied by our proportionality constant. And I'll just signify that proportionality constant as alpha here. And I'm not going to go too in depth on this proportionality constant. We have been given it in this problem, it's 0.1, but essentially it's pre-calculated and it takes into account different things like the piping size of our discharge piping into each tank. So here we'll just have the proportionality constant. Now if you'll notice, we have a little bit of an issue here because here in this problem
we may have, or actually most of the time we'll have that h1 minus h2 will be a negative number here because h1 will be less than h2. Well, we can't take the square root of a negative number. We'll get an imaginary number. So actually what we have to do here is we have to take the absolute value, the absolute value here. So we'll have the absolute value of h1 minus h2, still taking the square root. But here you'll notice that this may completely change our answer here for the flow. So when we originally would have a negative answer here, we now have a positive answer because of the absolute value. So what we need to do here is take into account the sign of this difference here between h1 and h2 so that it won't change our answer. So it's kind of a little bit of an algebra trick we can play here. So if we set this equal to the sign of h1 minus h2 and multiply that, and we can actually do this in Python when we actually do these calculations, it'll make a lot more sense. But essentially here, if we have the difference between h1 and h2 is negative 90, this sign here will just be negative 1. So we'll have negative 1 times the absolute value here. So our answer here will not change. So it may make sense, it may make sense, it may not make sense, but hopefully it will once we get into Python and we start doing the calculations. So the same flow equation holds true here for the flow from tank 2 into tank 3. So we'll have Q 2 comma 3. Again, we'll have to take the sign of the difference in heights, so h2 minus h3, again multiplied by our proportionality constant alpha, and then again taking the absolute value of the difference between heights and taking the square root of that, so h2 minus h3, and raising that to the 1/2 power. Okay, so these are the equations here for our flow. Now, what we'll want to do here for our differential equations, since we're just taking a look at the height of the different 3 tanks that we have here, we're not taking into account the concentrations of the contents that we may have flowing from one tank to the next. So if we're just looking at the heights here, what we can say for our differential equations is we'll have cross-sectional area A1. So if we're looking at the flow into or out of tank 1, we'll have A1, and we'll take the derivative of the height with respect to time. So here this will give us our change in volume for this tank here. So we'll have this equal to, well, let's see what makes sense here. The only thing that makes sense here is that we'll have flow from tank 1 going out into tank 2. So we'll have negative Q1 comma 2. So that's our differential equation here for our first tank. For our second tank here, so we'll have A2, again, dH over dt. So again, the change in volume over time. This will be equal to, well, let's take a look here. Here in tank 2, Q1, 2 will be positive because it's going into the tank. So we'll have Q1, or excuse me, actually, we'll take a look here at the Q in, since this kind of makes more sense if we're going in a more logistical approach. So Q in here, obviously we're adding Q in, so this will be a positive number. So our flow in, our initial flow in, and then adding our flow from tank 1, so adding the flow from 1 to 2, and then here we may be, or we will be here in this example, discharging flow from tank 2 into tank 3, so we'll have to subtract that flow value. So we'll have minus Q2 comma 3. Okay, now taking into account the change in volume for the third tank, we'll have cross-sectional area A3, again, dH over dt, change in height over time. So this will give us the change in volume. And here we'll have equal to, well, we'll just, actually I forgot to write this up here, but we'll have Q3 being the flow out of the third tank. So Q3 will be the flow out of the third tank. So here, the only flow that we can have in is the flow from tank 2 to tank 3, so that will be positive here. So we'll have Q2 comma 3, and then taking into account the flow out of this tank here, we will have minus Q3. Okay? So this gives us here our equations for flow from one tank into its successor tank, and the differential equations set up here for the change in volume for each of the tanks. So if we want to go ahead and talk about this so-called proportional control that this problem wants us to utilize, essentially what a proportional control setup looks like is, so if we want the fluid level here in the third tank to have a set point height of 4 meters, essentially what that's saying is we don't want to overshoot that set point to have like 4.5, 4.6 meters of level in that tank, but we don't necessarily want to have a really low level either. You can essentially think of that set point as a sweet spot. So if we want to go ahead and set up an expression for this proportional control, so I'll go ahead and write a proportional control here. So I'll go ahead and write a variable name for the set point of the third tank that we want to have here. So I'll write that as H3SP, so the set point height for the third tank. And what we can say here is that if the height of the third tank is less than the set point that we give, and here again, we have, the problem tells us that our set point here is 4 meters. So let's say that the height in this tank, so H3, is like 0.8 or 0.9 meters. Well, what will we need to do in order to increase the level in the tank to get closer to our set point here? Well, we will have to increase the initial flow into tank 2 in order to raise the level here. So what we can say here is that in order to increase Q in, we will have to take this here and multiply it by this Kc value. And this Kc value is what is known as a proportional gain. Now this proportional gain value here can be changed around in order to match up perfectly with different systems that you may have, but it can be utilized to fit any different system. So here we have our setup here, and we can actually use the information that we have here. Again, like I said earlier, we can use the solve IVP tool in Python in order to simulate this system here in order to determine and see exactly what's going on with our system.